Welcome back to our second and last video for the acids and base chapter here. We're going to start off here by talking about a very specific kind of reaction that acids and bases can have. This is what we call a neutralization reaction. And this happens specifically when you have something that is an acid reacting with something that is a base. And I know, technically speaking, every acid, when it reacts with something, causes the other thing to act like a base. We're talking more here specifically about things that are strong acids and strong bases, and we'll look at what that means more in just a second. But things that are essentially known to be acidic and things that are known to be basic. It's not that you have a really strong acid and it's forcing something that doesn't really want to act like a base to react like one. This is two things that are perfectly happy, one to act like an acid and one to act like a base. And in reactions like this, when we have a strong acid and a strong base reacting with one another, what is always going to happen is that when these two come together, so in our example here, we have hydrochloric acid and we have potassium hydroxide, both of which are strong either acids or bases. And again, we'll define that a little bit better here in just a second. When these react together, they will always make some kind of a salt compound. In this case, they make potassium chloride and water. Water is going to be one of the products of these neutralization reactions. The reason that we call this a neutralization reaction is because when you take a strong acid and a strong base and you react them together, these two things that are strongly one way or the other, the products that they make as a result of that reaction are neutral. They're neither acidic nor basic. Potassium chloride is not an acid or a base. Water is not an acid or a base. So you take these two things that are essentially net opposites, put them together, and you get a neutral result. And so the net ionic equation, if you remember that from earlier, I forget which chapter it was where we talked about that, but we talked about net ionic reactions versus complete versus just normal, so to speak, chemical reactions or chemical equations. The net ionic equation here is just H plus OH minus gives us water. Because if everything starts off in aqueous phase, and then the end result is that you still just have potassium and chlorine in the aqueous phase, they didn't really change at all. They're still just ions floating around in solution. The only thing that really changed was the H plus from the acid combined with the OH minus from the base to make water. And so these neutralization reactions, their net ionic equations are always just going to be the formation of water. Okay. And I do make a little point here pointing out that not every neutralization reaction works out exactly this way. If both of the things that are reacting are strong, it pretty much does. Everyone reacts this way. But since we are just kind of skimming the surface here in this class, for our purposes, we're going to assume that all of the neutralization reactions work this way. And if at some point in your life you need to know differently, someone will tell you. Let's take a look at example 14.2 real quick. So this says, write a molecular equation for the reaction between aqueous HCl and aqueous calcium hydroxide. So we have HCl, which is an aqueous solution, which is an acid, hydrochloric acid, and we have calcium hydroxide, which is also an aqueous solution, and that is a base. So I would like you to pause the video here and work out what the two products would be from these things reacting together and balance. the equation. It shouldn't be difficult to balance it. It's nothing too crazy. If you're getting like coefficients of 6 or 8 or anything like that, that's not right. It should be very simple to balance, but go ahead and balance it and work out what the two products would be. So go ahead and pause the video now and try to work that out. Okay, so we already mentioned in the previous slide that when you have a neutralization reaction where you have an acid and a base, one of the products is going to be water. So we know we're going to make that. The other product is essentially just whatever's left over, whatever you have left, which in our case is calcium and chlorine. And calcium and chlorine only come together one way, and that is CaCl2. If you remember our rules from earlier in the class, calcium has a +2 charge, chlorine has a -1 charge, and so you would need 2 chlorines to match the charge on the calcium, and so we have CaCl2 to get that neutral molecule, and this would be an aqueous phase. Okay, so those are our two products. The second step then, is it balanced? And it is not. If you notice here, we have calcium balanced, but chlorine is not. We have 2 chlorines here, only 1 here. So we know that we're going to need 2, let me erase that real quick. We're going to need at least 2 of those. Oh, oops, sorry. Wrong one. 2 of those. Sorry about that. Don't mean to confuse you. So we know we need at least 2 of the HCl's to match the chlorines here. So now our chlorines are balanced and our calciums are balanced. If we check the hydrogen and the oxygen, the hydrogen, we have 4 on the left, only 2 on the right, and we have 2 oxygens on the left and only 1 on the right. And so to get that to balance, we can just put a 2 in front of the water. That will give us 4 of the hydrogens and 2 oxygens on both sides. All right. So moving on here, I told you just a minute ago that we would talk a little bit more about what it meant to be a strong acid or a weak acid. So when we say that an acid is strong, what we're saying is not that the acid is really reactive. They are. All strong acids are very reactive, but that's not what it takes to be a strong acid or base. The technical definition of a strong acid or base is any acid or base that completely, keyword there, completely, ionizes in water. If it completely ionizes, it is strong. If it only ionizes partially or incompletely, then it is weak. And what I mean by that, if you're thinking, what in the heck is he talking about? When I say that it completely ionizes in water, is I'm saying that if you take perchloric acid, which is what this is, it is a strong acid. If you put, just for sake of simplicity, we'll use a small number, you put 100 molecules of perchloric acid into water. Every single one of those molecules is going to break apart into H plus and ClO4 minus. Every single one. If you put a lot more than 100, they will also, all of them completely break apart into H plus and ClO4 minus. All of the molecules will ionize, is what we call it, where they break apart into their 2 individual ions. A weak acid, on the other hand, would not. It would only partially do that. And when I say partially, I don't mean that it's going to be like half broken. What I mean is that, let's say again, we put 100 actually, no, let's do this. Let's do HC2 H3O2. That's one way of writing acetic acid. And so that breaks apart when you put it into solution into H plus and C2 H3O2 minus. But not every single one of them will do that. So for a weak acid, you might put 100 of them into the solution, and maybe just one of them breaks apart into the two ions. Could be more than just one, but it's not uncommon at all to have weak acids or bases where very, very few of them break apart into their ions. So a strong acid, every single last one of the molecules will dissociate, will break into its ions, and a weak acid or base, only some of them will. And it could be a relatively large portion. You could have something where maybe 10% of the molecules break apart. That would be a relatively strong weak acid. But there are quite a few acids and bases where you only might have 1 in a million or so that will dissociate, and those are still acidic or basic. They will still give you an acidic or a basic solution. They're just weak in terms of their ionization. So, speaking of these strong and acids and bases here, these strong bases, there are a limited number of these, as well as the strong acids. There's a limited number of those as well. The strong bases are all the soluble group 1 and 2 hydroxides. There are we've already seen one of them, the KOH, NaOH. Well, I guess you can see them right there. So these guys, essentially. These are all, just take these metals and pair them up with hydroxide. That is a strong base. The acids, on the other hand, they don't fit quite so nicely onto the periodic table like that. There are 7 that are strong acids, and all the rest are weak. So HCl, HBr, HI, those do kind of fit onto the periodic table nicely. But then we have perchloric acid, chloric acid, nitric acid, and sulfuric acid that are all strong acids, and every other acid is weak. Now again, when I say strong, I am not saying reactive, and when I say weak, I am not saying unreactive. There are some weak acids, like HF, for example, hydrofluoric acid, that is crazy dangerous and reactive. Extraordinarily reactive. Like, would kill you very quickly and painfully if you encountered very much of it. So when I say it is a weak acid, I'm not saying safe or unreactive. All I am saying is that if you put it in water, it doesn't completely ionize. Now, for our purposes here in this class, you do not have to have these memorized. If you were in my Gen Chem 1 class, I would have you memorize them, but we're not going to do that in this one. But I did want to point them out so you could recognize them if you needed to. Alright, let's look at a really quick, easy practice problem here. This says if we have a solution that is 1 molar HCl, what will be the concentration of the chloride ion in that solution? So go ahead and look that over, think about it, and pause the video if you need to, and see if you can figure out what the concentration of Cl- would be. If you need a hint, you should not have to do any math. So go ahead and pause the video and see if you can work that out. Okay, so if we have 1 molar HCl, if we go back to our previous slide here, that is a strong acid, which means it is going to completely dissociate. Every last one of those HCl molecules is going to give us an H plus and a Cl minus. And so what that means is we are going to have 1 molar Cl minus in our solution. Now we would also have 1 molar H plus. Because again, whatever concentration we started with, we're going to have the same concentration of the products here, because every single last one of these original molecules is breaking apart. And so whatever its concentration was, we'll have the same concentration of the products. Alright, real quickly here, to finish up this chapter, I want to talk a bit about the pH scale. So the pH scale comes from a really interesting reaction that takes place with water. If you remember in the last video, I kind of hinted that water can act like a base in some situations and an acid in some situations. It just depends on what it's reacting with. And I hinted a little bit that it could even react with itself. And this is actually a really important reaction, the reaction between water and itself. You can have two water molecules that will react with each other. One will act as an acid, one will act as a base, and produce H plus and OH minus as a result. Now this is not a really strong reaction. It doesn't produce a lot of H plus and OH minus in normal pure water at room temperature. You have just 1 × 10⁻⁷ molar concentration of both of these things. So it's not very strong. There's not a lot of this reaction happening. But just because there's not a lot of the reaction happening does not mean that it's not significant. That's actually very significant. Because this reaction happens in water, there is always some amount of H plus and some amount of OH minus. Even in the most pure water you will find anywhere, it will have some of both of these things. Not only that, no matter how much acid or base you put into water, there will always be some of both of these things. There will always be some H plus and some OH minus. If you put a whole bunch of H plus, a whole bunch of acid into water, there won't be very much OH minus, but you'll still have a little bit in there. There's always going to be some amount of both. And so what we do to measure the relative acidity and basicity of a solution is just to track those two concentrations. We track the concentration of OH minus and the concentration of H plus, and they are related to each other. They always go in opposite directions. If one of them is increasing, the other one is decreasing. You're never going to have a solution with a bunch of H plus and a bunch of OH minus. They would just react together to get back to what we call normal. They would neutralize each other, if you remember. There's always just going to be a small amount of one if you have a lot of the other. So in terms of acidic versus basic, right smack in the middle where you have a neutral solution, you would have 10⁻⁷ of both. And if you remember, I said that if we had pure water at room temperature, that's the concentration we have. This is what we would normally think of as pure water, neutral water, when we have 10⁻⁷ of both H plus and OH minus. Scientists didn't really like working with those concentration values, though. They wanted an easier way of dealing with these concentrations, and so what they did was they took those concentrations and they put them to a log scale. And if you're unfamiliar with what a log scale is, it's not super important for us right now, but essentially it just takes a number and you ask the question, what would I have to raise 10 to get this number? And that is the value of your log. And if you're really confused by that, it's okay. We're not going to be doing math with logs here. Just know that that's what this is called. It's called a log scale, and it uses the actual log button on your calculator there. So if you have an H+ concentration of 10 to the negative 7, that is going to have a pH, which is again on that log scale. Our pH scale is going to have a pH of 7. And if we come back here in just a second, but this is where we get that pH from. It's this equation here. If we plug 10 to the negative 7 into this spot right here, take the negative log base 10 of that number, we get 7. We get this number here. As you notice, it does stay consistent there. So if we have 10 to the negative 8, we have a pH of 8. If we have 10 to the negative 9, we have a pH of 9, and so on. So the lower the number, the more acidic the solution is. Because the smaller this number is, the larger the concentration of H+. So pHs that are less than 7 are acidic, and pHs that are greater than 7 are basic. You do not have to get all the way to 8 to be basic, or all the way down to 6 to be acidic. Just anything greater than 7 is basic, anything less than 7 is acidic. Did I say acidic twice? Anything greater than 7 is basic, anything less than 7 is acidic. And by the way, these do not cut off at 0 and 14. They can actually go beyond that, but you don't really find that in nature at all. Most things that you find in nature are within that 0 to 14 range. Okay, so just to give you kind of a few ideas of some pHs of different things that you might come across in your everyday life. Your stomach acid can range anywhere from a pH of 1 to 3, which is actually that's a pretty decent range, because with log scales, going from one unit to another is actually an order of magnitude. So going from a pH of 3 to a pH of 2 is actually 10 times as acidic. You have 10 times as much concentration. So that's a pretty good range. This is one of the reasons why some people have issues, is because they might have disorders with maybe having too acidic of gastric acids. Limes and lemons, pretty acidic. Soft drinks, a lot of people, thankfully, nowadays are more aware that soft drinks have stuff like phosphoric acid in it. Coke is pretty nasty. In terms of that, they put phosphoric acid in there. I believe that's what gives it its bite, is that phosphoric acid. It's not good to leave that on your teeth, for sure. Other things are a little bit closer to neutral. We'll skip over a few here. So human blood is actually slightly basic. If it was not slightly basic, you would be very much dead. The acidity or basicity of your blood is actually extremely important. You can see that the range here is actually really small. If you start to move outside of that 7.3 to 7.4 range, you're not going to die instantly, but you're going to be very sick quickly. If you get down to a neutral pH blood or a more basic pH blood, there are buffering systems in your blood that keep you where you need to be. Probably the most basic thing you have in your house is maybe some cleaning ammonia with a pH of around 11 or so. If you do have sodium hydroxide in your house, I hope you are like a soap maker or something. That's used pretty commonly to make soaps. Sodium hydroxide is really nasty stuff. It's very, very good at breaking down biological materials, which is you. You are a biological material. So if you do have sodium hydroxide, be careful with it. One quick last thing I want to point out here that most people don't realize, rainwater, which everyone thinks of this pure, beautiful rainwater from the sky. It's unpolluted. It's the most pure, and everyone just assumes that it's neutral pH. It is really not. Unpolluted rainwater. So this is like not in a city. If you live in a big city, it's even worse than this. But normal rainwater has a pH of around 5.6. It's actually decently acidic. Not so much that you have to be worried or anything, but it's not neutral, and that's from just naturally occurring gases in the air. CO2 in the air, for example, when it mixes with rainwater, makes carbonic acid, which makes the rain slightly acidic. Again, it's nothing to worry about. You don't have to run from your car to the house when it's raining for fear of being burnt. It's nothing like that. But it is something to keep in mind when people talk about, it's more of a dinner party conversation topic. People talk about acid rain, and you can pull this out of your back pocket. Like, did you realize all rain is actually acidic? So it's kind of a fun topic. More acidic than normal rainwater is actually quite bad. So if you do live in a big city where there's lots of sulfur and nitrogen in the air, and nitrogen, by that I mean like nitrogen oxides, not just into nitrogen pollutants, you can get sulfuric acid and nitric acid from those mixing in with the rainwater. So that's more worrisome. Alright, that'll be it for this chapter. I know this was kind of a long video, but I wanted to go ahead and just finish it up in this one. As always, if you have questions, feel free to reach out to me, and good luck with the homework. See you in the next one.